So last time we started proving this theorem. Okay, so our goal is to try to do something non-trivial with linear size proofs. Linear size, now we are in the IOP model, so we're adding up the sizes of oracles across interaction. Okay, and specifically we want to try to achieve want to construct an IOP for circuit satisfiability. It's actually arithmetic circuit satisfiability for large and smooth fields, where the number of rounds and the query complexity is logarithmic in the size of the circuit. So the proof is in 3 steps. Last time we have seen how to reduce CSAT to univariate sumcheck. Okay, we did it into 2 sub-steps. We first reduced CSAT to bilinear equations and then bilinear equations to univariate sumcheck. And we checked bilinear equations with those 2 sub-protocols. I mean, so we kind of bundled everything up into univariate sumcheck. So today we're going to see how to reduce univariate sumcheck to logarithmic testing, basically proximity testing to the Reed-Solomon code. And then we're going to start talking about an actual protocol to do that. Okay? I also noticed that so far we haven't really used the fact that f is large and smooth. We'll use it at some point. Questions?
What does smooth mean?
Well, when I what does large mean, right? So we haven't defined either. So univariate sumcheck problem is an oracle problem. You're giving me an oracle. For now it's promised to be of low degree. It's evaluated over the evaluation domain. And we also have this summation domain H. Typically it is smaller than L. We'll assume for simplicity it is a subset of L, doesn't have to be. And our goal is that if the sum of f over this summation domain is 0, then we want to accept with probability 1. And if it's not, then we want to accept with small probability. Last time we sort of discussed why straightforward solutions such as querying the set H directly or running the multivariate sumcheck protocol on a univariate problem didn't really make sense. So today we're going to see a different idea. Okay, so we're going to see a solution. Okay, so actually before we get to the solution, we're going to look at some apparently unrelated algebraic facts, where basically we're going to leverage some algebraic properties. And the first thing, we're going to assume that H is a subgroup of F star. Well, actually, it doesn't really matter of what, but let's say of F star. So we're going to assume that H is a multiplicative subgroup of the field. Now, if this is the case, let's maybe put them here. We're going to prove a Qt lemma, which basically relates the how polynomial sums over subgroups to its coefficients. Okay. So we're going to prove that, let's assume that D is less than H, okay, or at most H. And I'm also going to assume that the size of H does not divide the characteristic of the field. Okay. Then we're going to prove that if you sum F over the summation domain, then you get size of H, let's say F hat of 0. What does F hat of 0 mean? It means that you take F, you interpolate it, you look at the 0th coefficient. I don't see enough people nodding. Is it clear what I'm doing? So F is an evaluated code word, okay? So I can't talk about the coefficients of the function. What does it mean? I have to first interpolate. I'll call it f hat. That gives me a polynomial and evaluate it at the 0 point. Okay?
Well, the characteristic doesn't provide h, right?
I think that's fine, yeah. And the reason why I want that is because I want this expression to make sense. Okay? So actually, this looks like a very mysterious statement, but it's actually rather elementary. So let's first look at a simple case of a monomial, okay? What is a polynomial? Just a weighted sum of monomials. So let's just look at what happens with one monomial. If I take a monomial and I sum it over the summation domain, what's going to happen? So, so for a fixed I, if I sum for h in h, h to the I, that's basically asking what is the sum of the monomial x to the I over h, right? Now, because h is a subgroup is a multiplicative subgroup of the field, it must be cyclic. Okay, so let's use that fact. I'm going to write this as sum from j equals to 0 to h minus 1 of some generator omega. Okay, so the jth h is going to just be omega to the j, and this is to the I. Right? Okay, so I can just switch the powers. So I'm taking the sum of omega to the I to the j. So here I have a fixed element in the subgroup omega to the I, and I'm summing up all of its powers from 0 to h minus 1. So this sum can only really have two outcomes. Anybody have any guesses? Depending on I. So for example, let's look at the simple case. What happens if I is 0? No, if I is 0, here I get what? 1. And 1 to the j is what? And as if I sum it h time, what do I get? Right, so I get h if I is 0. That's really not the only case. I could wrap around, right? Because I'm in a group. Really, so if it's I is mod 0, I is 0 mod h. Right? Okay, suppose I is not 0 mod h. Then what's happening? I'm taking some non-unit element in the group, right? And I sum all of the powers up. And remember, I'm in a cyclic group here. What's going to happen? So hint, like these must be roots of unity. I should get 0, right? So if you kind of look in the complex plane and you sum up all roots of unity of some order, they all balance out and you get 0. Okay, so that's one. I mean, of course, to think of the complex plane, you would need to take the algebraic closure, right? But we are in a finite field, and these are roots of unity. So add them up, and you get 0. All right, is it clear? Okay, this is what happens just with one monomial. So it's basically saying whenever you have a non-zero monomial, you have x to the I where I is not 0, then you get 0. If it is 0, then you get h. Okay? So now, if I really was asking, what do I get if I sum f of h, then what's going to happen? Well, I can think about all of the monomials of f. Well, they all disappear except for the 0 coefficient, which is just the constant that sits in front the x to the 0, right? So I will get h times f hat of 0. Okay? So this is just telling me that if f has degree, that is no more than h. Okay, so here really remember that this d here, the definition of the here is that you have degree of f is strictly less than d. Okay, so just because that's h up to h minus 1. So if my f has degree that is strictly less than h, then the sum over a subgroup is entirely controlled by the zero coefficient, because everything else kind of balances each other out. It doesn't matter what those coefficients are. Great. Okay. But so this is under the assumption that the degree, let me just maybe write it more explicitly here, that the degree of f hat is strictly less than h. Okay? So let me state that we actually need to understand what happens when the degree of f is actually above h. Okay, and the reason is because if you remember last time we were invoking the univariate Sumcheck on a virtual polynomial q whose degree was on the order of 3 times n, right? And 3 times h, right? So we really have to handle the other case. And what we're going to do, we're going to try to reduce the high degree case to the low degree case. Okay? So what we're going to say is that if let's say g hat is congruent to f hat modulo the, so I'm going to write down this polynomial, okay? Polynomial, which is all the zeros. So I'm going to take the polynomial that makes up whose roots precisely coincide with the subset that I'm considering. Okay? If two polynomials are congruent modulo this relation, then their sum over the domain equal. Do we agree? Well, the proof is that g hat of x will equal f hat of x plus some multiplier times this polynomial. But when you take the sum, that polynomial just doesn't affect the sum. So this is to say that if, for example, the degree of f was high, I can always divide out by this polynomial and bring its degree to be less than h. Somehow I'm taking out a high degree portion that doesn't really affect the sum. Okay? So these two facts together now are going to immediately give us actually a solution to the univariate Sumcheck problem. It is actually a very simple protocol that incorporates both of these. But are we fine with the proofs? So I'm making two independent statements. First, I'm saying if I have a polynomial of small degree, then the sum is controlled by the zero coefficient. Secondly, if I have two polynomials that are congruent up to, modulo, this is called the zero polynomial of the subset H, then the way they sum over the subset is, over the summation domain is the same. Okay, kind of by construction, because like if they differ by a multiple of that one, then it cannot affect the sum. Okay, and obviously, taking modulo is one way to take your degree down, right? Because you can always pull out whatever multiplier was causing a high degree. So here's a very cute protocol. So the prover and the verifier. So now we're going to come up with a protocol for univariate Sumcheck. They have access to f. Okay. So what the prover is going to do is first and foremost help the verifier deconstruct f into the remainder g and the quotient h under division by the vanishing polynomial. How it will help it? It will just send g and h. It will say, hey, here is g, and here is h. Okay? allegedly the remainder and quotient under division by the vanishing polynomial. Now, of course, the verifier will have to test that a G is, what's the degree of G, by the way? That's the remainder. What should the degree be? H minus 1, right? Because I'm dividing a polynomial by a polynomial of degree h, so the remainder must have degree strictly less than that. And h has degree what? Yeah, f is degree minus h, and now f was promised to be of degree d, so I'll just take d minus h. And also I keep, sorry, I should really write here h, because by the definition here, it's strictly smaller, right? So, okay, so this is telling me that g and h are representing polynomials of the correct degrees. And then I also need to pick some alpha over L, and I need to check that these polynomials are correctly related. Right? But I haven't checked any sums so far. What I've done so far is that I have received 2 more words from the prover. I've tested them so that they are close to polynomials. And I've made sure that they are the remainder and quotient of f under division by the vanishing polynomial. But now really I'm interested in, my question now is, as a verifier, kind of at this point, the question that I have, since I know at this point that the sum of g equals the sum of f, and I'm interested in the sum of f being 0. Is the sum of g 0? That's my question now, right? I mean, I know through this test that the sum of g must be equal to the sum of f by construction. So now all I'm left to do is to make sure the sum of g is 0. But actually, this part uses this lemma, right? Or rather, yeah, forget that for a moment. We haven't really used this lemma yet, and I'm saying, okay, I'm wondering about the sum of g now because I'm applying this lemma for g, and I'm wondering, when is it 0? Well, when g hat of 0 is 0, right? Okay, but this equals 0 if and only if what? What does it mean that f hat of 0 is 0? The coefficient is 0. And in particular, I know that x divides f hat of x, right? If I evaluate a polynomial at 0 and it vanishes, it means that x is a root. Okay? Okay, I'm really not applying this onto f hat, now I'm now applying it to g hat, right? So what I'm going to do is I'm going to ask the prover not to send me g, but to send me g over x. I will tell him, please send me g prime. I will test that g prime has degree strictly less than h minus 1. And then in my test here, I'm going to myself multiply by alpha outside to force my g that now I'm creating myself. I will force it to have a root at at x. Okay? That's it. This actually makes sure that if this test goes through, it means that the sum of f is 0. Is it clear? It's kind of magical, right? The point is that this lemma allows us to kind of turn a sum into a coefficient and into a divisibility condition. Okay, some sort of polynomial identity test. And I'm testing whether x really divides, in this case, g hat, by just asking the prover to just send me kind of the other quotient divided by the quotient of g by x, which is g prime. And I check that directly here. Okay? So that's it. And kind of the soundness error, maybe just to kind of be clear, the soundness error overall is going to be the soundness error of this identity check, okay, which is what? So what's the error that I pay for here? So I'm sampling alpha from the domain L, right? And I'm checking what am I going to pay for? Excuse me? A little bit more than that. At least H over L, yes. D over L, right? Because I'm starting from F that has degree D. And for example, F participates in the left-hand side. Right, so I will pay for the maximum degree that shows up anywhere here. So here I have D. Here I have H minus 1 then times H, right? Here I have D minus H and then H again. So it's D, right? So it's going to be D over L plus, whatever noise I get from the low degree test, right? Because if the low degree test will give me 10% noise, I will pay for that. I'm doing multiple low degree tests here, so I'll just, it's not really needed, but I'll just put a constant here. You don't even have to pay for that constant, but it doesn't matter. Okay, so this is how you reduce univariate Sumcheck to low degree testing. This is a reduction, by the way, because even under the promise that F is low degree, we did use as a subroutine a low degree test. Okay, so I haven't technically solved it. I've just reduced the problem to low degree testing. Because inside the protocol, I have tests to do, these two. Okay, so this is a little bit different than, say, multivariate Sumcheck, where under the promise that your original oracle is low degree, everything I'm doing after that is sort of, there's no testing, right? It's just I'm exchanging explicit polynomials. Here, I'm actually doing some testing underneath. Well, nonetheless, here it is. I'll just mention a very cute open question, sort of whether is this or something like this possible when H is not a subgroup. So we know how to do this for multiplicative subgroups. There is some other similar things that hold when you have an additive subgroup. That's it, and we don't really know, what happens if you have other, maybe not necessarily arbitrary, but sufficiently nice H's. Okay, so it's a very nice question to think about. Okay, so that's as much I wanted to say on univariate Sumcheck. We are about to move earnestly into proximity testing, and it's going to get technical real quick. So are there any questions on this one before? Yes? We can't choose it, because it's a good question, by the way. Like, is this assumption really an assumption? It's not really an assumption in the sense that when I design the protocol, I get to decide over which domains I am interpolating over, because I have this information about the witness and I get to encode it over whatever sort of subset, and then I interpolate that. So I have that power. The question of, and then so why would you ask this question? Well, because it just gives you more flexibility, right? So it could be that it's difficult for me to find, I may have to pad until, the next reasonable size to create a subgroup, right? But instead, maybe I really wanted this size, right? So having more flexibility in my choice of H is just more convenient. It also teaches me more about what's going on here. Right? But asymptotically, kind of, there are subgroups, and I just need to make sure that I have subgroups that are sort of dense enough in the size of my problem. This is one of the reasons why smooth here comes in, because if you want f star to be highly composite as a size, then you need to make sure that you can pick an h that is linear in n.
So it should be characteristic of f divides h, but the characteristic of f is always a prime, so this doesn't make any sense.
This doesn't make any sense. Yeah, it's a prime.
Actually, it
Yeah.
doesn't matter apart from the conclusion, like the main conclusion.
You mean this one?
Yeah.
Yeah. This is true either way, right?
Yeah,
But for this part, I need it. I'll just point it here.
Yeah.
There we go. Thank you, Nick. Okay. Okay. So now we're left with the clean subproblem of I give you a word over L, and I'm asking, is it anywhere close to the Reed-Solomon code? Okay. All right. So now my input to the problem are the parameters f, L, D. These are kind of my explicit inputs. This is the field, this is the evaluation domain, and this is the degree bound. I have an oracle. Now it's not promised to be anywhere, it's just an oracle. And the goal is that if f is inside the Reed-Solomon code of degree D, then I want to accept with probability 1. And if instead the distance between f and the Reed-Solomon code is, say, at least delta, then I want to accept with probability at most, say, some epsilon as a function of delta. Okay? So I have this problem. We've seen similar things before when we discussed linearity testing and low degree testing for multivariate functions. And in fact, we have already seen this problem when we discussed multivariate low degree testing. We actually started with univariate low degree testing as a special case, right? So we have seen two things. We have seen that D+1 queries suffice for getting epsilon delta to be equal to 1 minus delta. And the test was basically just interpolate any D points and check consistency at a random other location. Okay, so basically we're taking any D points in a domain, for example, the first D points of L, you interpolate, you get a polynomial, and now you pick a random point in L, and you compare whether F and your interpolation agree. Okay, and we actually analyzed, like a few weeks back, that what you will get is your soundness error is kind of as good as it gets. Okay, namely, your acceptance probability will go down with as your distance increases. Okay? So the farther away you're from the code, the smaller your acceptance probability is. Okay? It's kind of also optimal. And we also saw the number of queries that the DP+1 queries are necessary for epsilon of delta to be strictly less than 1. Because because any D values extend to a code word in the Reed-Solomon code. Right? I really need to ask d+1 queries, because if I just ask d queries, whatever answers I get back, I pass a polynomial, and I will get a view that is consistent with something that was in the code. So there's no way I can make an informed decision from that, right? So we've already seen this, right? And so this state of affairs is problematic because for us the degree is linear in the problem size, okay? So we really can't deal with a linear number of queries in D. In fact, our goal is going to be log D, which is exponentially smaller. But fortunately, you know, both of these statements were in the case of when I don't have a prover to help. I was just asking, let's just test the code word by myself. Okay? Now, I'm in some interactive protocol. I can ask the prover to send me auxiliary information, for example, other proofs. Okay? And maybe through these other proofs, I'll be able to do better. Okay? So this is inherent that we have to leverage interaction with the prover, or some help from the prover, because of these reasons. We've seen this before, right? So are there any questions about this? The definition of the problem or either of these statements? Okay. So, okay, so we're gonna, going forward, we're gonna restrict our attention on a special type of Ritz-Solomon code, which is over smooth domains. I'm actually going to define it now, what smooth means. I'll state what we know in terms of state of the art, and then kind of what it is that we want to prove. So let's call RS star to be the problem where we have our input and the oracle. We are in the Ritz-Solomon code. So I'm defining a restriction of our problem. And now I want to put some properties on L. Okay, and the properties that we're going to study today are that L is generated by omega, okay? And it is a subgroup of F star. And also I'm going to take the kind of order of omega to be a power of 2. Okay, all I'm saying is that let's restrict our attention to the Ritz-Solomon code, where the domains are generated by are basically multiplicative subgroups of order that is a power of 2. Okay, now we'll see in a moment why this is the case, but right now, just to jump the gun a bit, is that this is very helpful, the same way that it is helpful to do FFTs over multiplicative subgroups. Okay, fast Fourier transforms are these recursive things that are defined over objects that look like that, and the reason why we restrict our attention to these objects like this is basically for the same reasons. Okay, so an important theorem from 10 years ago says that for this problem, we can actually construct, even non-interactively, pretty good PCPPs. So I can tell you roughly. So the length is going to be L polylog L, and the query complexity is going to be polylog L. Okay. This is basically saying that, yes, we need help from the prover, but it doesn't have to be interactive. We can just get by with a plain PCPU proximity where on top of the code word, I just send you some L polylog L amount of information, okay? And that will help you check your code word with a polylog number of queries, which is much better in D, okay? This is actually a key component of a result that I only stated before, which is it's a key component of so-called short PCPs that basically say that n time t is contained in PCP, where L is t polylog t, and Q is, say, polylog t. Last time there was a question about where do short PCPs come from? Well, for example, this is a key step, okay, showing that there are short PCPs of proximity for the Reed-Solomon code. But we're shooting for linear size, okay? We're shooting for linear size. So even this is not good enough because we have polylog extra factors, okay? So what we're going to see is a theorem, just actually from a couple of years ago, that gives an incomparable result in the IOP model. And it says this smooth Reed-Solomon has IOPPs, so IOP of proximity, in the parameter regime that we care about. I mean, the parameter regime that we stated there is precisely inherited from this point. So we're going to have the number of rounds is going to be log L. The length is going to be linear in L. And the number of queries is going to be log L. Okay? So notice that this log linear log regime is precisely the one that is stated here. And the reason is because those parameters are sort of bubble all the way up through the reductions that we've seen so far, right? The reductions we've seen so far basically cost nothing. They cost linear things and constant blowups. Okay? So somehow these parameters are for the most part determined by whatever you achieve here. So you can view this as basically the algorithmic core of that result. So we're going to study, so the reason why we want to see this is because at least we can see one construction where we achieve linear size. It's also a beautiful construction. It looks like some sort of a randomly folded fast Fourier transform. It's also of practical interest. It's a very efficient protocol. Conducting this protocol can be done actually in linear time by the prover. So it's one of the best tools that we have today for proximity testing. Okay. So the goal for the rest of today, and indeed all of the next lecture, is to talk about this result, which is admittedly a little bit more complicated than what we've seen so far. Okay, but it's still beautiful, so I think it's worth to go through it. Questions? Okay, so I'm going to give a couple of broken attempts at the protocol. And then I think by the time we get to the protocol, it will be clear what the protocol is trying to do. Okay, and then we'll analyze it. I think today we'll only get around to discuss broken attempts. Okay? So, yeah. So the key idea is basically to take inspiration from the divide and conquer approach of the radix 2 fast Fourier transform. So the radix 2 fast Fourier transform is just the one that you see normally in undergraduate courses. For example, in CS 170, that's the algorithm that we see. And key here is like divide and conquer. Okay, so the kind of the first step. So let's just recall for a moment that algorithm, the fast Fourier transform algorithm. So we view a polynomial as odd and even coefficients, right? So we're going to take a polynomial, And we are writing it as f of x equals g of h squared plus x times h of x squared. Okay? So these are the even coefficients, right? And these are the odd coefficients. And then the fast Fourier transform is based on the FFT is based on a simple observation that if I want to evaluate f on L, which is generated by omega, okay, it suffices to evaluate G and H on L squared, which is generated by omega squared, okay? And then combine the results. Okay, so and the way you combine them, if you remember, you just look at and put down the formula so that sort of feels familiar. Right, this is the way there's a linear linear time, linear combination, where you take the results from G and H, and you combine them. So over all of them are, you have two results of size n over 2 each, okay? And you combine them into the result of size n, okay? So this is the FFT algorithm. Right, because as omega sort of takes on n different values, omega squared takes on n over 2 values. Okay? Okay, and an important aspect is that we have this nesting of domains. We have L contains L squared, which contains L to the 4th, which contains L to the 8th, and so on and so forth, right? That somehow, because you have evaluated these two sub-problems on a subdomain, you're able to, in linear time, extend it to the bigger, twice as large domain. And of course, the recursion, the number of times that you recurse is r, which is log d, right? So at some point you finish, you have 2 to the r. Okay? Okay, but we're not evaluating things. We're doing low degree testing, so what? The point is that from the perspective of low degree testing, we can also try to think in divide and conquer, okay? Where we try to take a low degree testing problem for degree d and try to reduce it to a low degree testing problem of degree d over 2. And ideally, if we do this over log number of iterations, we'll get to a constant size problem we can solve, okay? So let's see kind of where this takes us. So, from the perspective of low degree testing, the main thing that gives us any hope is that the degree, if the degree of f is less than d, then that's equivalent to saying that the degree of g and degree of h is less than d over 2. Okay? So if f has a degree that is strictly less than d, then we know that g and h, the polynomials induced by the even and odd coefficients, also have degree that is less than this time d over 2. And conversely, if I know that they do have small degree, then when I combine them, I get f that has small degree. Okay? Somehow, this decomposing of the problem respects degrees in a way that we like. So this immediately gives an idea, a first attempt. Okay, it's going to be broken in many ways, but let's see how. The first attempt will say the following. We have the prover and the verifier. Both of them have access to the original problem, f. And the first idea is to say, look, the prover will just send G over L squared and H over L squared. Okay? First and foremost, it will make sure that they make any sense. Okay, so it will sample mu from L and check that f of mu equals g of mu squared plus mu h of mu squared, to make sure that really they are the odd and even parts of f. And if that's the case, then okay, they're related in the right way. Let's recurse. We're gonna invoke ourselves to check that G is in the Reed-Solomon code where I have f, L squared, and d over 2. Okay? And H is also of degree d over 2 over L squared. Okay? This is I've specified a test. Okay? So, anyway, what's the problem? Let's start like this. Anybody see a problem with this test? So our goal here was to reduce the number of queries. How many queries are we asking in this test? What? It's too many, right? It's L, right? Because if we write the recursion, we have Q of L, right? Equals, well, how many queries am I asking in this round? It's 1, 2, 3, right? Plus 2 times Q of L over 2, right? Because that's L squared. But that's, that's linear in L. So that's not good, okay? So, in fact, it's even deeper than this in a sense that, so I'm going to explain that even if we're saying we're fine with paying linear number of queries, maybe you could say, maybe that's a different construction that gives us the same guarantees as that one. Okay, maybe it is just a linear query test that actually is testing. Okay? And maybe we can use it as a springboard for something better. But I'm going to claim that it's not even a test. It is making a linear number of queries, obviously, but it's not even a test. And I'm going to convince you of that. Okay? Meaning it's really actually not doing logic testing. It's somehow, it's too weak. And that's important to understand the direction in which we need to go next. Okay? So, another problem, just as serious, if not more, is that we can say that the proximity parameter it decays from delta to delta over 2 to delta over 4, and it becomes subconstant very quickly. So let me show that with a picture. So suppose that f has, let me make it big. So what? That's f, and this is g, and this is h. Okay, so f is over L, and g and h are over L squared. So suppose that we have the following setting. G will have say 5 errors out of 50. So I'm saying, suppose L squared has size 50, which means that G is 10% corrupted. Okay? And now suppose H is also 10% corrupted. It has 5 errors out of 50. Okay? So this is basically saying that I need to make sure that my testing proximity as a subroutine is tuned to make sure it can detect 10% errors. Ideally, I would like to say that if my test passes, for a subroutine, I want to conclude that f is also within 10%. Okay? But that's not going to fly, because if you see kind of what's happening here is that when I combine G and H, you could have a test that passes completely, a consistency check that passes completely, and yet f is corrupted at twice as many locations, even relative to the twice as large size. So here we have 20 errors out of 100, and that's 20%. Meaning that, what is this telling us? This is saying that it is possible for somebody to give us a corrupted word here, there is 20% corrupted, and pass the consistency check with 100% probability, and have G and H be actually closer to being a low degree. And as these rounds go, kind of these smaller and smaller subproblems are creeping closer and closer to low degree, even though I started pretty far. And along the way, I have no chance to catch it. So kind of my proximity test is decaying. Okay, that's a big problem. So even if I enroll this test, it's actually not testing anything. It is making a linear number of queries, but it's not testing anything. So, so this is it's a very serious problem, right? And this is telling us that in this proximity testing world, taking a log number of rounds, we have to be very careful, okay? We could be picking up problems at every round, and we have a super constant number of rounds, we have many, many problems, more than we can handle, okay? So our second attempt is going to attempt to deal with both problems together, okay? The second attempt we can call it random folding. The idea is as follows. So we again have the prover. Here's the verifier. They share the function f. As before, the prover is going to send a G and H. And as before, the verifier is going to sample mu from L, and it will check that f of mu equals G of mu squared plus mu H of mu squared. But now, the verifier is going to take another move, and it's going to say, hey, here's a random alpha in the entire field, okay? And we're going to recurse in a different way. We're going to check that G plus alpha H is inside Rs f L squared d over 2. Okay? So what does it mean by that? I think of the virtual oracle, G plus alpha H. Actually, I actually want to instantiate it. I think it's going to be easier. The prover sends me f sub alpha, okay? And I'm going to test consistency of f sub alpha. I can do it at the same point. So f sub alpha at mu squared, it should equal G of mu squared plus alpha H of mu squared. And now I'm going to test that f sub alpha is inside the Reed-Solomon over L squared and d over 2. Okay? I'm reusing the same randomness, it's fine. Okay, let's first observe that at least now, syntactically, the number of queries is fine. Why? Because the number of queries well, in each round, what is it going to be? Well, I touch this one, I touch this one, these two, say 4 per round, right? But now I'm recursing on just one subproblem. So overall, I get that it's log L, right? So at least that part is fine. But why would I think that I made progress with this problem? Okay? Which was a pretty serious problem. So, first I need to at least convince myself that this is fine even without errors, certainly convince you of that, okay? And then we're gonna see that with errors, we did make progress with this problem, okay? So first I'm gonna do kind of like a very baseline analysis that says, let's suppose there are no errors anywhere. Am I even making sure that this one doesn't have too small of a degree? Okay? The question here, does folding make sense? Wait, the reason why I'm calling it folding is because I'm kind of folding G on H according, around the pivot alpha, right? So okay, suppose all functions are actually polynomials, no errors. Exactly. So certainly for every alpha that I send, the degree of G plus alpha H is at most the maximum of degree of G and degree of H. Do I like this? Yeah, that's nice, right? Because we already agreed that the good G and H go down by half. So it means that in the good case, the honest prover can indeed be safe that for every alpha that I send, G plus alpha H will have degree that is D over 2. Okay? And now, it's not really soundness, but just to build intuition, the probability over alpha that the degree of G plus alpha H is strictly less than the maximum of the degree of G and the degree of H is actually at most 1 over F. Okay? So again, forget evaluations of polynomials. Let's say we're talking about polynomials, so that there are actually, like, I'm handling things with coefficients, okay? So what's the proof? Well, in this sum, look at any monomial. Doesn't matter if a high degree or low degree. Look at any monomial that it appears in either G or H, okay? This monomial has a 1 over F chance of disappearing at most in this expression, right? Because it could be that it is too high up and either polynomial doesn't touch it, so it certainly will stick around, or it gets interference from the other polynomial, but to the extent that it gets interference, the only way it can disappear is when alpha precisely equals minus of the other thing. That will happen only 1 over F of the time, okay? So, so there is exactly one choice of alpha for which a given monomial disappears. In particular, if you think about the monomial that is responsible for the maximum degree, this monomial will stick around with probably at least 1 minus 1 over F. So this is basically telling me that at least without errors in sort of this exact polynomial fantasy world, random folding makes sense. Yes, I'm paying for some sumness error, but it's 1 over F. And over log L rounds, that's not much, right? That's log L over F. So that's fine. well, in the fantasy world. So now let's see whether this problem even went away. Okay. So so let's say, what about with errors, right? Well, now things look actually a bit nicer. So let's plot f. So this is just intuition, okay? So the analysis is will come in a bit. So we have f, g, h, and their random sum. Okay? Now, let's put in f, g, and h the same setting as before. Okay? So g is corrupted on 5 out of 50 places, which will cause f to be corrupted on these 10 places. And h is corrupted on these 5 places, which will add up another 10 places to be corrupted in f. So that's the same example as before. But now we're not testing either g or h. We're testing a random linear combination of g and h. So what we expect to happen, ideally with high probability, is that I will have both of these around, right? Kind of the errors will, the fact that the errors are out of sync, they're not in the same locations, the random linear combination will suffer from that. Okay? And so now this one will be corrupted in 10 errors out of 50. That's 20%. So that's the same proximity parameter I started from. Okay? Somehow this folding is kind of making sure, it's not just making sure that my queries don't blow up, it's also making sure that errors align. Okay? Making sure that my proximity parameter doesn't decay. This is just intuition, of course. Okay? But the point is that folding helps with proximity and queries together. Okay, or at least it seems like it does. Okay, the analysis that this is the case, again, will come in a bit. All right, we still have problems. Okay, so let me discuss a problem of this where we are at now. So we have a problem that kind of, so we lose too much in the consistency checks. So proximity was one problem, queries was another, we fixed them. But now if you unroll the recursion, what's happening? At each round, we're doing a consistency check between f, g, and h, and then between f sub alpha and g and h. Okay, and we're doing this at every round. Now, each of these, we can really hope to have constant accuracy. Okay, I mean, the prover could cheat on, I don't know, 5% of the locations and start, being inconsistent, and I will catch him with probability that is proportional to how many errors he planted there. Okay? And he can do this independently every time I'm conducting a consistency check. So, if whenever I sample mu in L in the first round, I pay, I don't know, 2% accuracy, then, when I sample mu squared in the next round, I pay again 2% accuracy. I'm being very generous here. I continue like this. At the end, I will have a total of, 2% to the r, where r is the number of rounds. But that's very small, sub-constant. Okay? So, if before the prover could cheat by creeping closer to the degree, now he can just creep away from the function I was discussing. Okay? I cannot keep him close to this kind of random folding of the original function, he can start, slowly moving away to, I don't know, random folding of other functions, okay? Because, again, it's okay to run a few of these tests, but I'm learning log of these tests, okay? So that's problematic. Do you feel that? So the solution, it's actually a kind of, I think that, until this point, it is a rather natural, and I would not say a simple design. But now comes, I think, like a very sort of a powerful and to some extent non-trivial idea, is that we're going to design one single test that is global. It's all correlated, okay? We're going to think of a single global consistency test of all the things that were sent, and this global consistency test will have constant accuracy by itself. Okay, kind of all this mu squared, blah, blah, will not be IID. They will actually be connected. Okay? Actually here, it should have been mu prime. They will all be connected into one big global consistency check that we will argue have constant accuracy. Okay? If you think about it sort of ex post, that's kind of, there's no other way to escape it, okay? The moment you're going to uncorrelate these consistency checks, they will each have their own errors, and they will multiply, okay? So the solution is going to be we design a single global consistency check that we will show has constant accuracy. Now, okay, that's all sound fine, but where is it? Like, why do we expect such a thing to exist? So let me give you some intuition for why such a thing might exist by arguing that actually I don't even need to send the G and H to you. Okay, somehow I know them already. Okay, I can fold in my head. So let me first argue that. Okay. So first we're gonna make a simple observation. So to design the test, let's sort of see a couple of things. The first one is that I'm going to define an operation, fold, of f and alpha. Fold of f and alpha is a function from L squared to f. Okay? I want to argue that this folding operation is actually a local operation on f. I can actually query the folding of f myself just with access to f. I don't need to give me G and H and for me to do a consistency check. So first I'm going to give a formula and then I'm going to justify it, okay? So I'm going to define it. Fold of f and alpha is going to be at a particular point mu squared, okay? It is going to be f of mu plus f of minus mu over 2 plus alpha f of mu minus f of minus mu over 2. Okay, I'm defining this one. I'm defining a folding operation, and I need to convince you that whatever this thing is doing, it's the same thing that we were doing here with G and H. Okay? Claim that fold of f hat alpha as a polynomial. So I take the polynomial f hat, I fold it, equals a g of x squared plus x h of x squared, or rather, sorry, plus alpha h of x squared. Okay? And in fact, I'm also going to put a y here because really I can actually talk about an entirely bivariate object. Okay? That's what I'm going to claim. What? Here? I don't think so. but now we're going to see why. Okay? So we're going to see it now. So I know that f of mu, or rather, I am thinking in my head, I'm viewing f of mu as g of mu squared plus mu h of mu squared, right? I know that. I also know that f of minus mu is, again, g of mu squared minus mu h of mu squared, right? So g and h is what I really want to think about, right? And whatever they are, they satisfy this system of equations, right? Now, g and h, if you think about g and h as two variables, I have two linear equations in two unknowns, g and h. I mean, rather, g of mu squared and h of mu squared, right? So that's my variable, that's my variable, that's my variable, that's my variable, right? I can solve this system of equations, and what I will get is that g of mu squared is, I sum and divide by 2, f of mu plus f of minus mu over 2, and h of mu squared, I have to subtract, no, sorry. I sum and divide by 2, yes, then I have to subtract, yes, f of mu minus f of minus mu divided by 2. Therefore, if I'm interested in g of mu squared plus alpha h of mu squared, which is this f alpha, right? Then what is that? Well, it's exactly, this expression plus alpha times this expression, right? So I can fold in my head. Yes?
Sorry, just to follow up the same question that was just asked, doesn't there need to be a factor of mu in the bottom? Okay. Your low should mu over.
Oh, I totally lost on you. Thank you. Mu. On both of them, no?
Only on the minus.
Oh, sorry. Yeah, you're right. So, thank you. It's just here, right?
Yeah.
Thank you. And I think that I have it nowhere in my notes. So there is a mu here. Thank you. Okay, good. So, and the point is that this folding, it's kind of a local operation. I'm wondering, I wonder what is the value of folding f around alpha at a particular mu squared. Well, I know I can reconstruct it. Okay? So this is the main observation that lets me write down a plausible protocol. Okay, so we're going to write it down. It's actually not that complicated. I'll write it here. And then next time, we'll start analyzing it. So I will start with f, which I will call it f0, because we'll have functions coming down. I'll start calling it f0. I don't need g or h, so the prover will not send them. I'll send alpha, in this case alpha 0. Send alpha 0. Then he's going to send f1, which is from L squared to f. Now, allegedly, f1 is when you fold f0 around alpha 0. Okay? Then I send alpha 1. All of these are random, okay? The prover is going to compute f2, which is folding f1 around alpha 1. And he sends f2. f2 is from L to the 4th to f. Send alpha 2, and we continue until I send alpha r minus 1, and he sends me fr, which is from L2 to the r to f. As a verifier, I'm not doing anything until the very end. Remember, I'm doing a global consistency check. Okay? Well, first, at the very end, I should check that fr really is in the Reed-Solomon code of where it should be. I mean, I need to anchor somewhere the protocol, so this is, I'll check that, okay? And then I have my global consistency check. I will sample a single mu in L. That's all the randomness that I'm sampling. And from here onwards, everything is fixed. What I'm going to do is I'm going to say the following. Let's fold F1 around alpha, F0 around alpha 0. Evaluate it at mu squared, because remember, when I fold, I'm over the next domain. And I check it against F1 mu squared. I fold F1 around alpha 1 and evaluate it at mu to the fourth. And I check it against F2 mu to the fourth. I continue in this way until I fold the last one, which is Fr minus 1 around alpha r minus 1. And I fold around mu to the 2r. And I check it against Fr mu to the 2r. Okay? So I'm doing a check throughout. Each of these checks, if you expand this, I'm not really folding the entire function. I'm looking at just at mu squared, right? Because I'm looking at just at mu squared, I need to query only a couple of points on the prior function and 1 point on the next one. Okay? So pictorially, what's happening is that F0, I touch it at mu and minus mu. And I compare them against what happens at F1 at mu squared. And then I also query it at minus mu squared to compare it about what happens at mu to the fourth at F2. And I compare it, and then I also query this one, I continue like this, right? You see, all of these are correlated checks. Okay. So this actually is the protocol, okay? And so first, are there questions syntactically? Yes?
How is it different than just using the same mu for every round in the other protocol?
So here I am, that's a good question, but I also have this error between F and G and H, okay? And actually, I don't know whether one can handle that. Yeah. Though to some extent, kind of it's irrelevant because you don't really have to, like what you really were interested in was F sub alpha. Like I am uninterested in querying either G or H separately. And indeed I can't, because like here I'm saying that you can actually query linear combinations of G and H, right? So what I'm really interested in is to continue with this random linear combination. I don't really need to talk about either G or H. Here, G or H were just serving as a, they're serving the purpose of letting me fold, right? But if I can fold already in my head, I can just skip that part. It's kind of, you know, whether it suffices or not, I guess doesn't matter, right? Because I don't need it.
You're reducing just the number of queries, but are you actually decreasing the error?
Well, with that we don't know yet. We need to analyze. But at least right now, what's happening is that all the positions that I'm querying are correlated, okay? So what the analysis will have to show is that, you know, with constant probability over the original sort of problem, right? So if you're 30% far, then let's say with 30% probability, you will find the problem either in the first round or in the second round or in the third round, somewhere, okay? But the analysis will not look like, well, you have a 30% chance of catching in the first round, but if you don't, or rather, you have the 30% times 30% times 30% chance of catching it across all rounds because that's too small, right? So that's kind of the analysis that we're going to do next time. And the analysis is actually quite non-trivial, but I actually do want to do it as an example of a protocol of practical interest that is actually very fast. Again, I don't know whether if we keep around the other check, whether it would be fine if we keep it correlated, but certainly we don't need it because kind of all we really wanted was to fold. We didn't care about G or H specifically. Okay, so this is the test. So next time we're going to have a difficult analysis, but it will fit inside the lecture of this protocol. I encourage you to kind of look at it at home and make sure you're syntactically familiar with it. And actually, Nick and I spent a long time trying to compress. Like if you open up the original paper, it actually doesn't look nothing like this one. It's much more complicated. But I think we have like a very a reasonable presentation of the protocol. Like I hope this one was intuitive, and of the analysis next time. But I think it will help also if you spend some time offline to kind of redo the attempt and get to this final form. So the next time we can just get started with the analysis. Okay? Great. Tomorrow, make sure you send me, those of you who haven't, your preferences for the presentations, and then over the weekend I'll send out a schedule. Okay?